Hi there students, welcome back. In this part 2 we're going to look at perpetuities and then an introduction to some of the population models. In this first example we're going to look at a pension fund. We've got a fund value of 5 million rand, and what we're wanting to do is withdraw money as a perpetuity. So please understand, let's just go back. So please understand, when we're talking about a perpetuity, this is sometimes known as a living annuity. What we're wanting to do is we want to take out money at a regular period, but this money must last indefinitely. So we sometimes say the money continues as a monthly withdrawal forever, in perpetuity, carrying on forever. Okay, so just understand that if you've got a certain amount of money, which I'm going to say the PV, this is amount of money invested now. If you take a percentage of that and you're just taking out what the interest is, then that is going to give you a regular withdrawal amount. It's a very, very simple formula, but if you stop to think about it, you're just taking a percentage or the interest rate of something, remembering that this R is a rate per period. So if you wanted to take out, and I must just have a look here, yes, this one's a monthly allowance, then I've got to make sure that I've got a monthly rate. If you want to take out money annually, then I'd have an annual rate. If you want to have something taking out a certain amount of money every quarter, it would then be a quarterly rate. So the rate, just like all the other financial work, is the rate per period. So over here, this little formula, and just understand we might have to rearrange the formula. I like the formula like this. For me, it makes perfect sense. I'm just taking a percentage of the amount. I'm just taking out the interest every single month. If you have a fixed deposit and the interest gets added and you take out the interest, well, you can carry on doing that forever without your present value or deposit amount ever diminishing. But we might also ask another question saying, how much did you have to deposit now at a certain rate so that you can always take out X amount at this interest rate? And so we might have to rearrange the formula to solve for different unknowns, but I see it over here as the basic formula, and everything for me is based on that. Okay, so let's clear up and let's just see how I go and do this answer. So all that you do is you take your 5 million, you multiply by the interest rate, but because I wanted a monthly, this rate is a rate per month. So we can take out this is 50,000 every single month at a rate of 12% per annum compounded monthly, and we will never ever diminish our principal amount. Let's look at an introduction to recursive sequences. Remember why we do recursion. It is an introduction to population models. But if we just look at this formula here, Tn is P times Tn minus 1 plus 2 times Tn minus 2 minus 5. We always introduce the starting variables. And then what we should be saying to ourselves is, hang on, whoa, what's going on here? We should be saying where n is greater than or equal to 3. It tells me where I can start doing some input stuffs. So that would mean that T3, if n is 3, is P times T, or 3 minus 1 is T2, plus 2 times 3 is 1, 2 times T1 minus 5. And so we realize that the first term and the second term would combine to give me the third term. And then the second and the third would combine to give me the fourth, and so on and so forth. So just look very carefully here. We've got first term, second term, third term, fourth term, and they want me to go and solve for P and Q. So start off by setting up some initial equations. Very easy. I'd already shown here. You're going to say, well, T3, go put it in, but you have the value of T2 and T1. Okay, remember T2 was was Q over here, and you knew that T1 was 3. They had also told me that the third term, so if I just go back a page, they told me that the third term was 7, and I also had the value of the fourth term. So there is equation 1. Then I go and put 4, which means P times T3 plus 2 times T2 is minus 5. We know what T4 was. That value had been given to us. And then I can go and put in the different values. Okay, so I knew that T3 was 7. So I go put it over there. I knew that T2 was this Q. Rearrange, and then you've got 2 different equations. Now they're not nice equations, but they're also not crazy equations where you are going to go and solve simultaneously. My advice would be to isolate the q, substitute into the other equation, which you're going to notice you get to a quadratic. As soon as I get to that quadratic, I'm going to go and use my calculator. But I haven't gone and shown all the working. In your own time when you watch this video again, please make sure that you do get the right answers. Okay, I've used a calculator, and so you get a value of p that corresponds with the value of q, and you get another value of p that corresponds with a different value of q because it was quadratic. Now what we're going to do is we're going to model an annuity using a recursive rule. You could model the balance outstanding, you can model the future value, you can model all sorts of things. So just make sure that you play around and you're comfortable with this. Just in this example, I'm going to be looking at the outstanding balance. So you've got a loan of 20,000. There's a 15% per annum monthly rate. Okay, it was per annum compounded monthly, so this is normal. That's great. So when I go and work out R, which is the rate per period, I know that's just 15% divided by 12. I know that there's a monthly payment, so this is a fixed payment, and we want to create a recursive rule for the outstanding balance. Now, please remember there is something called an amortization schedule. And an amortization schedule says we've got some loan amount. This loan would grow with interest, so we'd be adding interest, and then at the end of the month we would minus some payment. This now gives me a new loan amount. This loan amount that I've now got, I would be adding interest, and at the end of the month I would subtract a payment, and so this thing just repeats itself all the time, so it's not too difficult to go and model it on a recursive rule. So look what I've done. I've said we start off with a loan of 20,000. In the very first month, this loan of 20,000 would have grown at a rate of 15% per annum compounded monthly. So this is just 1 month's growth. I don't have to show that. And then we would have minus this 850. And that would have then given me the new balance at P2, which then it would have grown and I would have subtracted the 850. And so now we can generalize this by saying, hang on, Pn plus 1, which is the balance at any one stage at the end of the month after your last payment has been made, or the starting balance at the next month. You're growing whatever the outstanding balance is, whatever the current population is, whatever the current financial value is, by a rate, subtract that 850. And so there is my formula. I just want to take a break and pull up my calculator so I can show you a few things. So if I just pull up my calculator here, I can say, all right, what is my initial population? My initial population is 20,000. Press equals, and now that's storing as the answer. And then I'm going to say, okay, well, the population, whatever it is, now is going to grow at that 15%. And of course, write 15% if you prefer. And I want it per month. And then I minus 850. This now will tell me this is the balance outstanding at period 2. And each time I press equals, it's giving me the balance outstanding at the next successive increment or the next population cycle. And here we're going in cycles of months. So this is the balance outstanding every single month. And we've created a recursive rule which the calculator can then go and model. All right. Let's go back to our presentation. We're now going to look at a Malthusian model. Now, a Malthusian model, for all intents and purposes, is just compound growth. That's all that we're doing. And there is a growth rate, which is your R, which is going to increase the population. And it assumes that there is no bound. The population just keeps growing and growing and growing. And we're working, like with compounding, in a specific time period. So it is exponential growth, it's compound interest. Sometimes instead of using a recursive rule, I actually prefer to use a compound interest formula. I find it easier to solve for some unknowns. So if you look at the textbook, you will see sometimes it actually serves you better to use compound interest. Then we've just got a couple of things. The growth rate is constant. This change in population over population, which we're going to see a number of times which is a significant part of a logistic model. This is known as the growth rate. The change in population versus the population is a growth rate, and this is a constant growth rate. It's like saying when we compound something, there is a constant interest rate as we go further and further and further. And then the other thing is we're going to talk about the intrinsic growth rate. Well, the growth rate is the difference between the birth rate and the death rate. So generally speaking, after each population cycle, a certain amount of the population will die, a certain amount of population will be born. The difference between that is the growth rate, which is how the population will continue to increase. So let's look at an example here. This is very similar to the one in the textbook. We've just changed some numbers. There they talk about a spider mite. We've got a female of a certain species is laying eggs. Now, it's very, very important because when we play with the growth rate, you should always be looking at, okay, how many, the number of eggs or the number of offspring. You're saying to yourself, okay, what percentage are female? Because that usually is a big part of the reproductive growth and the intrinsic growth rate. And then what percentage survival? Those are always the three things that I'm looking at. So this female will lay 35 eggs. Don't worry about a 15-day life cycle. That'll make sense of itself. The nice thing here with the Malthusian is usually there is just a single species. So everything is just working on the life cycle of this species. When we get to predator-prey and there are two different animals which might have a different life cycle, there we tend to standardize, usually 2 months, but the question will always be quite clear in the exam. So we're working on a 15-day life cycle. Female spiders, so we know what percentage are female, which is important, 75%. 55% of these survive. So that's going to enable us to go and work out the intrinsic growth rate. But please remember the intrinsic growth rate must also take away the death rate, which in a Malthusian model is 100%, because everyone dies off and then we hatch the next set of spiders in this case. Okay, what model can be used in this situation? There is no ceiling. There is no carrying capacity. This is just exponential growth, so it's a Malthusian model. Now, the really important thing that I want to stress here at B is we're starting with one female. We are not starting with a population. Okay, so I'm going to show on the next slide how we go and work with that. And then they tell me there's 120 days. So remember, we've got cycles of 15 days, so we know what the period is, and then we can work out how many cycles we're going to have. And then finally at part C, it says, what percentage of eggs must survive so that we get to a steady state. Remember, a steady state, also sometimes known as equilibrium. Well, the equilibrium occurs when the change in the population is 0. So we know that the population from one cycle to the next is exactly the same. So in other words, the birth rate is equal to the death rate. And that's how we get an equilibrium here. All right, so we know that this was Malthusian. We're going to work out the intrinsic growth rate. So the intrinsic growth rate is the birth minus the death. The death rate is 100% of the population are going to die out. Now, please remember, this is the number of eggs, the percentage that are female, and if I remember correctly, this was the survival percentage that are, survival. Okay, and so now we have got over here the growth rate. This is the intrinsic growth rate. And so I can create my model, Pn plus 1 is equal to 1 plus, okay, the intrinsic growth rate, because this is a compound interest formula, times whatever the population is. And now we know that the cycles are every 15 days. If you have 120 days, there are 8 cycles. But there's something that you've got to be so careful of in your final exam. You see, you started off with one female. You cannot start off with a population of 1, because that is a female. It is a sample. It isn't a certain ratio of these are female and a certain, 75% are going to be female and so on and so forth. So you've always got to go and generate the first population manually. What that means is Okay, you had one female, she's laying 35 eggs, and then there are going to be 55% chance of survival. There are going to be 19 eggs. We know that built into that is a certain percentage that are female, but there are 19 that are going to survive. So look how I've created this first population, and we generate that manually. Then that is going to be the population that goes into here, which is P1. Now I want to go and do this on a calculator again so that you can get to see what I've done. So if I just go, whoops, sorry. If I just go to my calculator, I just need to see. So we are starting with a population of 19 equals, and then I say to myself, well, that is going to be the population that changes. So that will go in as the answer. Open my bracket, 1 plus this intrinsic growth rate, 4,375, close it. Now we've got to understand we've already generated the first population. So when I press equals, excuse me, this is the second population, which I can see there. Third, fourth, fifth, sixth, seventh, eighth population. And we'll see, that's exactly the same value that I had over here. So just be aware of that and be able to use your calculator. And this is, I'm just going to see how many decimals. This is sort of 2,484,263,000 and some change. And then just the final thing that we do here is we talk about how do I get equilibrium or steady state. That's when the birth rate is equal to the death rate. And they said what percentage of eggs must survive to maturity. So I knew how many eggs, I knew what percentage were female, and then I'm just going to be solving for this unknown here, which is the survival to maturity, and I know that this product has to be equal to 1, because if the death rate is equal to 1, I want the birth rate to be equivalent to the death rate. And that's not too difficult, and then I can go and solve. Now let's look briefly at a logistic model. So a logistic model occurs when you've got a graph where you are looking at the change in population over population versus the population, and this is a straight line decreasing function. I'll repeat that. We know that we have a logistic model if you model the change in population. So this is known as the change in the population. And it's the rate of change, okay? If this rate of change versus the population is a decreasing straight line graph. And it should make perfect sense that when we are tending towards the carrying capacity, the rate of change tends towards 0. And so the change, or the rate of change, is 0 at this particular point here. And so we can read off the carrying capacity K as the x-intercept value of this function. And over here, right at P0, the initial population, its rate of change, its growth rate is going to be over here. So the y-intercept is the R value. And it's not too difficult. If I said, hey, how would we draw the straight line graph? What do we know? The gradient, M, is going to be negative, because I can see it's negative, and it is going to be the rise over the run times by your x, which is population. All right, whoops, I've just said that was the gradient. And then if I put that into the formula over there, we can see that that gives me a straight line. Change in population over population is some gradient times by the population plus some R. More about this just now in the third part. So what's the big difference between Malthusian and logistic? Well, a Malthusian assumes that there is no upper bound and we just carry on, and that there is enough food to sustain the population. We'll just continue growing because there's no predation at all. A logistic model starts off like a Malthusian model, but then it says there is going to be some carrying capacity. There will be some amount that regulates the population. And so this beautiful S-shaped curve, sometimes it'll go above, sometimes it'll come below, but it actually should be tending towards that carrying capacity. And so over here, this is the recursive rule that we deal with. Knowing that there are some parameters here, so the R is still the intrinsic growth rate, K is the carrying capacity, and P is the population. And what we should notice is that whenever we're going from one population to the next, it always says, well, what was the previous population plus the change in the population? And so this component here, the second part, represents your change in your population. And we'll just do one last example before we take a short break. So over here, we've got the rate of change modeled. We've got a straight line graph, which is great. We know 100% this now is a logistic model, which is great. They say, what is the intrinsic growth rate? The intrinsic growth rate is the initial growth rate. So that would be the y-intercept, which is nice. We can read there straight away. What is the carrying capacity? Well, the carrying capacity is when the change in the population tends towards some equilibrium value. So we know that the carrying capacity is the x-intercept, which isn't too hard to work out from a straight line graph. And then they say, what is the growth rate? Well, remember, this is the growth rate, which is your y value, when the population is 100. Well, that's just saying, when x is 100, what is the change or the growth rate of the population? So if I just put in some values, we could see that the y-intercept is your r value. The carrying capacity, well, you would just be finding the x-intercept, so you make this equals to 0. Take this 0,0317 over and divide by the 0,0002, and we go and solve for the x-intercept, which is the carrying capacity. And then they said to me, what is the growth rate when the population, which is your x value, because remember your x-axis is your p, when the x is 100. And so we've just substitute that into my formula. Not too difficult to show. That would then be the growth rate. All right, let's take a short break.